for proactive environment management. A design for high availability will consider the elimination of single points of failure and/or the provision of alternative components to provide minimal disruption to the business operation should an IT component failure occur. The design will seek to accomplish three primary objectives. First, the elimination or minimization of the effects of planned downtime to the business operation normally required to accommodate maintenance activity and the implementation of changes to the IT infrastructure or business application. Two, recovery criteria should define rapid recovery and IT service reinstatement as a key objective within the designing for recovery phase of design. Three, the utilization of fault-tolerant devices which make all reasonable attempts to recover from exceptions encountered within or from lower-level components. They will not allow invalid data from their clients to introduce errors into their own state. When a system is built using these high availability components, overall system robustness will significantly increase service availability. Having identified single points of failure, the designer can decide on what kind of redundancy, if any, is required. To approach continuous availability in the range of 100%, that is greater than 99.999% or 5 nines, requires expensive solutions that incorporate full redundancy, the technique of improving availability by using duplicate components. For stringent availability requirements to be met, these need to be working autonomously in parallel. Full redundancy designs add architectural components to increase load balancing, failover, and redundancies to system configurations. Measures include 1. Effective state recovery mechanisms. If a component fails, the system has to recover whatever state that component held before it can process new requests that need that state. 2. Careful tier design can help isolate faults. For example, a business component can fail without affecting the availability of the web front end until the front end needs to use that component. 3. Strategic failure handling. True high availability requires cooperation between the application and the application server. Likely types of failures that applications won't handle automatically need to be anticipated and failure handling built into the application. Lastly, clusters are comprised of multiple computing resources that are each capable of operating independently. As such, clusters have an inherent level of redundancy built in, enabling the system to be set up so that it provides uninterrupted application availability. Clusters can be configured such that even if a node fails, the rest of the nodes simply pick up the additional workload and continue without interruption. The failed node can be repaired or replaced, and while there may be a small decrease in the system performance, the end user will continue to have access to their applications. Designing for high availability in many systems requires a balancing act between proactive and reactive treatments. The system designer must first ensure that faults happen as infrequently as is economically possible, but the designer must also assume that they will nonetheless occur and take precautions to ensure that the system recovers quickly. The question is, which precautions are necessary? To answer that, the designer must first determine which services in a system actually require high availability and what degree of high availability each service needs. Once that has been decided, the designer can begin identifying any potential single points of failure, that is, any component, be it a CPU, network card, power supply, or software module, whose failure can cause the service to fail. For non-survival critical applications, the trade-offs are often financial. While the organization may target for continual availability, the costs implied in implementing fault-tolerant and total redundancy to remove all single points of failure can be exorbitant. The correct trade-off between availability and recovery strategy is illustrated in this diagram. Beyond a certain point of uptime, the costs begin to increase at exponential rates. At a certain point, it may be more effective to invest in recovery strategies. That point will be determined by the extent of losses incurred by the line of business when outages actually happen. The organization's ability to make an accurate assessment of these trade-offs is contingent upon its ability to assess the business costs of unavailability. That is, the losses incurred when systems and services are in various degrees of unavailability or degradation. Because of the costs associated with implementing high availability, it should be a comprehensive effort. Care and attention should be given to determining business availability requirements to accurately assess how much unavailability can be tolerated and under what circumstances. The ability to do this determination accurately is vastly furthered by a mature service level management process. The service level management process would encompass the assessment in a negotiation process wherein added availability is discussed in the context of the additional costs of delivering it. The trade-off would be subject to a negotiation exercise which recognized this and encompassed within an overall availability plan wherein individual availability needs could be packaged into an enterprise assessment, thereby achieving some economies in purchasing and support. A large array of tools and techniques have been developed over the years to assist in the analysis of service and component availability. The traditional IT approach would be to measure individually the availability of each of these components. However, the true measure of availability has to be based on the positive and negative impacts on the vital business functions on which the business operation is dependent. This approach ensures that service level agreements and IT availability reporting are based on measures that are understood by both the business and IT. All events and incidents causing unavailability of service and components should be investigated, with remedial actions being implemented within either the availability plan or the overall service improvement plan. Trends should be produced from this analysis to direct and focus activities, such as service failure analysis, to those areas causing the most impact or disruption to the business and the users. Service failure analysis is a technique designed to provide a structured approach to identifying the underlying cause of service interruptions to the user. Component failure impact analysis can be used to predict and evaluate the impact on IT services arising from component failures within the technology. The output from a CFIA can be used to identify where additional resilience should be considered to prevent or minimize the impact of component failure to the business operations and users. A single point of failure is any component within the IT infrastructure that has no backup or failover capability and has the potential to cause disruption to the business, customers, or users when it fails. It is important that no unrecognized single points of failure exist within the IT infrastructure design or the actual technology, and that they are avoided wherever possible. Fault tree analysis is a technique that can be used to determine the chain of events that causes a disruption to IT services. Fault tree analysis in conjunction with calculation methods can offer detailed methods of availability. This can be used to assess the availability improvement that can be achieved by individual technology component design options. To ensure if new components within the design can match the stated requirements, it is important that the testing regime instigated ensures that the availability expected can be delivered. Simulation, modeling, or load testing tools to generate the expected user demand for the new IT service should be seriously considered to ensure components continue to operate under anticipated volume and stress conditions. Risk analysis management is a technique that can be used to identify and quantify risks and justifiable countermeasures that can be implemented to protect the availability of IT systems. The identification of risks and the provision of justified countermeasures to reduce or eliminate the threats posed by such risk can play an important role in achieving the required levels of availability for new or enhanced IT service. It is essential that all availability mechanisms are tested in a regular and scheduled manner to ensure that when they are actually needed, they really work. All IT components should be subject to a planned maintenance strategy. The frequency and levels of maintenance required varies from component to component, taking into account the technologies involved, criticality, and the potential business benefits that may be introduced.